Let's run through a few quick examples where we are asked to find the most general antiderivative of each given function and prompted to check our answer by differentiation. We'll start with something nice and simple. F of x equals e squared. Don't let the e throw you off here. This is a constant, so its antiderivative would need to be something that just leaves us with a constant when we take the derivative, and that would be we see, we don't have a variable given here, but f we're told is a function of x, which means that our constant would need to be multiplied by x. And don't forget that whenever trying to find a general antiderivative, we need to account for the possibility of adding any other constant. We traditionally call that c. You can call it pretty much whatever you want, but c is the most commonly used variable there. So let's take a look at this and imagine taking its derivative and make sure that we get what we started with. The derivative of e squared x with respect to x is just e squared. The derivative of a constant is 0. So this function is the antiderivative of the given function. If we take a look at something a little bit more complicated, f of t equals 3t to the fourth minus t cubed plus 6t squared all over t to the fourth. We have a quotient here, and we don't have a quotient rule for derivatives. Antiderivatives, not really. If you're thinking about the quotient rule from derivatives, that doesn't apply here. But some techniques can be carried over. Hopefully, by this point, you have learned that if you were taking the derivative of a function that looked like this, you wouldn't actually want to use the quotient rule. That is excessively complicated. You should instead divide this t to the fourth into each term. So let's do that here and see what happens. Doing that division, simplifying it algebraically, we get 3 minus 1 over t plus 6 over t squared, which we can also write, it's good for, different things are good for different purposes. This is also 3 minus t to the negative first plus 6t to the negative second. So we have those two forms to look at. Now when we try to find the antiderivative of this, we say, okay, our first term is 3, that's a constant. Our variable is t, so the antiderivative would be 3 times t. We have minus this 1 over t, or t to the negative first. If you immediately recognize what 1 over t is the derivative of, so much the better. If you don't notice it, and you try the power rule, you'll discover if you add 1 to the exponent, you get t to the 0 power, and then try to divide by that, you have division by 0. That does not work. Even though this can be written as a power function, the power rule does not apply in this one case. Instead, we recall that 1 over t is the derivative of the natural log of the absolute value of t, right? And we have to then add for this last term here, we get, let's work through this. We have this constant 6, and that is being multiplied by, there's a t to the negative second. Here we can use the power rule. If we add 1 to the power, negative 2 plus 1 is negative 1, so that is t to the negative first, divided by the new power, which is negative 1. So we have 3t minus the natural log of the absolute value of t. Or this negative 1, when we resolve that with the 6, we get minus 6 t to the negative first, which we could write as 6 over t if we wanted to, whichever way we want to do that. We have this thing here. Let's check briefly to make sure that this works out. If we take the derivative of this, the derivative of 3t is 3. The derivative of the natural log of the absolute value of t is 1 over t. We have that. 6t to the negative first, its derivative, the negative 1 would pop out, making that a plus 6. And this drops down to a t to the negative second, giving us that. So this is the general, this is sort of the basis of our antiderivative, but we're not finished yet. First of all, we want the most general antiderivative, so we need to remember to add a constant. But it's even worse than that, because when we look at this function in its original form or one of these others, we see that this is actually defined for all real numbers except 0. And this is true about the antiderivative as well. This is undefined at 0, but it's defined for all positive real numbers and also all negative real numbers. Because it's undefined at 0, that breaks the two pieces of this. So this is only one of the possible pieces or sort of branches of the function. And there will be another one. There can be, I shouldn't say that there is, but there can be another one with a different constant. Those two are sort of disjoint here. And so this is if, let's just say if t is positive and if t is negative, it doesn't really matter which one we write where, because we get those two. The only difference at this point is the constants, so we can write that. Of course, once we have this, we can simplify further. It's nice to get rid of absolute values when it's possible to simplify those away. If t is positive, then that absolute value doesn't matter. The absolute value of t is t. So we get this. Whereas if t is negative, then its absolute value is its opposite. So negative t would then be positive. And this then is the general antiderivative, which is kind of beastly, but that's what we get. If you wanted to give this a name, since we had initially small f of t, you could call this something like big F of t, if you did want to give it a name. This is somewhat arbitrary. Just making a function letter capital does not automatically mean it's an antiderivative, but in this section, we don't have a lot of other notation for this. A better notation will come next chapter. So for right now, we just kind of make do and just kind of give these functions another name when necessary. But this part right here would be the general antiderivative in question. We take a look at another one. We have this function r of theta equals the secant of theta times the tangent of theta minus 2e to the theta. To find its antiderivative, we'll take each term in turn, and we look at secant theta, tangent theta, and we think about this. Say, okay, well, do we know a function whose derivative is secant theta, tangent theta? And in fact, we do. The derivative of secant theta is secant theta, tangent theta. Right? And we say, okay, we have minus 2 times this function e to the theta. Okay, well, what has e to the theta as a derivative? Well, e to the theta. Right? So we have this. We expect a constant. Let's look at this and say, okay, what happens if we differentiate this? Derivative of secant theta is secant theta, tangent theta. Minus 2, the derivative of e to the theta is e to the theta, so that matches up. Derivative of a constant is 0, so this looks good. Except, again, remember that we have discontinuities, right? Secant theta and tangent theta are each discontinuous at pi over 2 plus or minus some integer multiple of pi. So we actually have infinitely many distinct intervals here. We could say that this is plus the constant c sub n on the interval. And let me come up to the side to kind of sketch what I'm doing. They might have a little bit of difficulty seeing what I'm talking about. Remember that secant theta and tangent theta both have vertical asymptotes at plus or minus pi over 2. But if you go another pi units out to like 3 pi over 2, for instance, or another pi units this way to like negative 3 pi over 2, we have these regular intervals. And whatever this function looks like, I don't know offhand what it's going to be. It's going to do, something. Let's see here. So the secant would do that minus, blah, blah, blah. Let's just suppose it looks, I don't know, something like this, maybe. Might have something like that. And then you might have, if this were just secant, you might have something coming down this way, but we can have any constant added to that. So maybe it goes like that. And maybe over here we have one down like this, or, whatever, right? These are each independent pieces. They can each have their own constants. So we have an interval from basically negative pi over 2 to pi over 2, but we also want to add n pi to that. So you have negative pi over 2 plus, or let's say pi n, up to positive pi over 2 plus pi n. So this interval for any integer value of n and some corresponding constant c sub n would describe the general antiderivative. Now, don't worry, in practice, next chapter we'll see a convention where we just sort of assume an antiderivative only works on an interval, so you're not going to have to constantly work out all of these elaborate intervals every single time you need an antiderivative for a problem. Most problems will have at least one sort of reference point or anchor point where we can figure out what's going on, so they don't always get this messy. I'm just trying to show you some of the worst cases you might run into in terms of constructing these intervals. In most cases, we won't have to worry too much about those intervals, and we're mainly concerned with figuring out what the antiderivative is. But like I say, sometimes they get a little bit, the intervals can get a little bit messy. But most of the time, it's just a matter of, okay, figure out what the antiderivative is, make sure it's defined where we need it to be defined, think about the domain, continuity, things like that. One last quick example here. We have f of x equals 2 plus x squared over 1 plus x squared. This one, again, like I said, we do not have a quotient rule for antiderivatives, so this is a little bit formidable. One thing we might do is, since we notice that these have the same power, you could use polynomial long division and get this into a quotient and some other part. Or we could just work with this by inspection. 2 is 1 plus 1, so we could split this apart and make it look like 1 over 1 plus x squared plus 1 plus x squared. That looks terrible, let's fix that. 1 plus x squared over 1 plus x squared, right? So if we simplify a little bit, and so this first part stays how it is, and then the second one is just 1, right? Well, none of my other ones look like that. Let's take that out. Let's do that. So a little bit of algebra, we get it down to this. And like I said, if you didn't notice, you could just pull it apart like that. That's fine. You can do polynomial long division, and you should get a quotient of 1 with a remainder of 1, so you can write it as 1 plus 1 over 1 plus x squared. This helps us because now hopefully you recognize that first term is the derivative of the arctangent, the inverse tangent of x, right? So that is the antiderivative of this. 1 is the derivative of just x. And again, we need a general constant. So let's look at this and make sure the derivative works. If we take the derivative of arctangent of x, we get 1 over 1 plus x squared. The derivative of x is 1. The derivative of a constant is 0. So this is an antiderivative of this function. Do we need to break this up at all? Well, let's look. Where is this continuous or discontinuous? Well, the only place this could be discontinuous is if the denominator equals 0, but if x is real, the denominator is never 0. So this is actually just one continuous interval over the entire real line, and that's it. There's your antiderivative. Like I said, we don't usually have to do a lot of messing around with different constants on different intervals. It's only when we have a break in the domain. But if the function is continuous everywhere, or it's only defined on a single interval, then we only have to worry about one of these, and the tricky part is figuring out what the antiderivative is. So here's a sampling of a few different techniques you might run into. Most of it at this point is going to come down to the question of looking at the function you're trying to find an antiderivative of, and ask yourself, okay, does that look like any derivatives that I know? Make sure that you know your derivatives, but if you know your derivatives solidly, think through, okay, does this look like anything I know? And if it doesn't, try to see if you can do some algebra. and we'll work something out from there. But that's pretty much how this type of problem works.